Hello, let us start our lecture. And the first topic, we continue investigate the Poisson process. By n lambda of t, I will denote the Poisson process with parameter lambda. So n lambda of t for each fixed t has Poisson distribution with parameter lambda times t. We have discussed some properties, and let me recall you that Poisson process n lambda t can be obtained from Poisson process with parameter 1 by time transformation. For example, it can be easily seen. Indeed, this process is process with independent increments. This process is a process with independent increments. Increments of these and these processes are Poissonian and stationary. So the distribution are equal, and if we know properties, so we may simulate Poisson processes only with intensity 1 and then make some time transformation and in properties of Poisson process with parameter lambda. uh, the last time we proved that if you consider this process, well, I will not write 1, and I will assume that if I don't write 1, then intensity is 1, that n lambda t divided by lambda converges locally uniformly to t with probability 1. So probability that for every t you have this as lambda goes to infinity is 1. And immediate corollary is corollary about this. Certainly we have convergence in distribution. So for this process we have the following convergence, and lambda t divided by lambda converges to t locally uniformly in probability. So what does it mean? That for every t positive, excuse me, for every t probability that supremum n lambda t excuse me, over lambda minus t converges in probability to 0. Indeed, probability that the supremum is greater than epsilon is the same as supremum for this difference, and we know stronger result for n lambda t divided by lambda, so we have this convergence in probability. The third property is analog of Donsker theorem, and the result is the following. If you consider Poisson process, subtract expectation and divide by square root of lambda, then this process converge divide by square root of lambda converges to the Brownian motion as lambda goes to plus infinity. In the space of Cadillac functions. In if I write 0t, then 0t in the space of Cadillac functions in 0t. A little bit later, I will introduce metric on the space of Cadillac function on 0 infinity, and the result will be the same. Okay, let's discuss how to prove this and how to use usual Donsko's theorem and in order to prove this result. Well, we know that for every sequence of IID, eta n means 0 variance 1 t over square root of n converges to a Brownian motion in the space of continuous functions. Poisson process is not continuous. Well, here it's not so difficult to prove that you also have this. If lambda may take non-natural values. And we agreed that we extend random walk by linearity to non-natural numbers. So let's see the random walk here. So let's denote eta k, let eta k be n of k plus 1, eta k minus eta k minus 1, and let me write like this, plus k minus 1. So compare with the numerator here, or n k minus 1, oh, excuse me, minus 1. So if we consider this eta case, then we may see that as eta n for natural number n is equal to n of n minus n. So S of eta lambda n divided by square root of lambda coincides with this process if lambda t is integer. So S eta lambda t over square root of lambda is equal to n of integer part of lambda t minus integer part of lambda t divided by square root of lambda. And we know that this process converges to Brownian motion. So in order to prove that this process converges to a Brownian motion, it is sufficient to prove that the difference between this and values of this process in integer numbers converges to 0 in the following sense. So let's prove that n lambda of lambda t minus lambda t over square root of lambda converges in probability to 0 as n goes to infinity. And then we will use the following result. This converges to Brownian motion in the space T, in the space D of in the space C, excuse me, of continuous functions. And this difference converges to 0 in probability. So the distance between these and its linear approximation converges to 0 in the space D. We know that uniform distance is greater than or equal than distance in the space D. And then we apply the following result that we have discussed. If sequence converges to X in distribution of elements in certain metric space, and if distance between Xn and Yn goes to 0 in probability, then Yn also converges to X in distribution. And this is the case. And now, what is the maximal value?
Excuse me,
Yes.
can you please go back for a second?
Yes.
Can you please tell what is S eta n now?
Yes. S eta n is n of n minus n.
Okay. We
Yes.
we make random jumps with when I'm walking with eta, yes?
So I consider eta. So I consider Poisson process only in natural times, and then I make linear approximation. Well, and I consider this process. So n of n, yes, n of n minus n. And this process is, so this sequence, excuse me, this sequence. So this sequence is sum of increments. So this is sum k from 0 to n minus 1 eta k plus 1 minus eta k plus 1. Or if I sum from 1, okay, sum from 1 to n, from n, k minus 1 plus 1. So this is a sum of increments, and all of these random variables are independent and have the same distribution. Which one? Poisson distribution with parameter 1. Well, and minus 1. Okay, so this is a distribution.
Yes. Okay, thank you. And we have we have expectation, distribution,
and
everything.
I subtract here 1, and now expectation of this is 0, and variance is 1. So I may apply Donsker theorem for this random walk in this form. And my question is, what is the maximal difference between this and this? And I wish to find the maximal distance between these two sequences.
Here n is without lambda, just
yes, n without lambda. Yes, and then I multiply. Then I consider all t, multiply by lambda, divide by square root of lambda, and send lambda to infinity. But I recall that I extend all random walks by linearity.
Okay, thank you very much. It's clear.
And now here the explanation that if we show this, then it suffices for our proof. And let me make a picture of this process. So what is Poisson process? Well, it is jump time process, so it waits certain amount of time, then jump by one, then again jump by one, and so on, and so on, and so on. And now assume that we consider the process n of t. So this is n of t. Then I want to consider the process n of t minus t. So like this, then I jump, and then subtract t, then I jump at the same moment, subtract t, okay, and so on, and so forth. Okay, so this is my this is my process. Oh, and okay. So here is 45 degrees. And then I make scaling divided by square root of lambda. And this process coincides with the initial one in all natural points. This point, okay, this natural point, this natural point, this natural point, and so on and so forth. What is the maximal difference between this and this process? Well, so this maximal distance is attained only in natural number. Oh, in well, natural number, it is not attained, maybe, but
When we approach to the natural number.
so let me write the inequality. So I state that, well, let me consider for simplicity, okay, in 0t n of lambda t minus lambda t minus n of lambda t minus lambda t integer part square root of lambda. It's less than or equal, well, different, this and this is less than or equal to 1. And difference between this and this is less than or equal to sum of n n of k plus, no, not sum, maximum at k plus 1 minus eta k, increment of Poisson process if the difference between two times is less than is 1, divided by square root of lambda. And we take maximum over k. So k is now lambda times t. And t between 0 and t, so k less than or equal to lambda times t. And these are ID random variables. So let me write like 1 over square root of lambda plus maximum psi k less than or equal to lambda t. And let me denote like lambda t is mu, k less divided by mu. Then square root of lambda is square root of mu. And maybe square root of t here. And I know that psi k have Poisson distribution, IID, but the more important thing that the expectation of square of psi is finite. And we discussed that if the second moment is finite and you take n or mu, these random variables, then maximal converges to 0 in probability as, well, lambda or mu goes to 0. So we used this property. And this completes the proof. Well, here I used previous results. Certainly,
Excuse me,
yes, yes.
lambda mu goes to infinity.
Lambda goes to infinity, yes. So for this difference or the proof of Donsker theorem, you may use another properties of a Poisson process. So actually we used the only one property, that n is a process with independent increments, such that every increment of this process is mean 0, so expectation is 0, and variance is finite. And that's all. There are analogues of Donsker theorem for martingales, and there are a lot of results on this topic. Okay, but now let us continue. Let us continue, and let us discuss some problems related to Poisson process. And let's discuss the following problem. The statement: if n lambda of t and n mu of t are independent Poisson processes with intensities lambda and mu respectively. Equation: what is the distribution of their sum? Igor, Gennady?
Poisson process with intensity is their sum.
Yes. Why?
It was on the previous lecture.
Okay. V is intensity lambda plus mu.
But we have not proved just
It's that's simple because this is a process with independent increments and stationary increments, and we know that sum of
Poissonian is
is
Poissonian.
Poisson, yes, and when we add and parameters, we add parameters when we add independent Poisson. And now the next question. Okay, let me example. Let n lambda t and n lambda tilde t be independent Poisson processes with intensity lambda. Question: what is the scaling limit of the following process? The difference divided by square root of lambda. Okay, solution. So what do we know? And I would like to recall you that n lambda of t has the same distribution as this. And n lambda of t minus lambda t divided by square root of lambda has the same distribution as n lambda t minus lambda t over square root of lambda. And we know that this converges to a Brownian motion, so this converges in distribution to a Brownian motion. And this process has the same distribution, so it also converges in distribution to a Brownian motion. And now we consider difference and let me write it like n lambda of t minus lambda t over square root of lambda plus n tilde lambda t minus lambda t over square root of lambda. I know that this converges to Brownian motion and this converges to Brownian motion. These two sequences are independent, so I may write the following. The pair of two independent processes. Well, I know that if they're independent, we discuss this property, and if each coordinate converges in distribution, then the pair converges in distribution. So it converges to Brownian motion, another independent Brownian motion, and t goes to infinity. And now, well, I wish to say that addition is, or difference is continuous in the space of Cadillac functions. Actually, this is not true. Nevertheless, I make cheat a little bit and prove that the difference converge to difference of two Brownian motions. Indeed, let's apply Skorokhod representation theorem, and we know that we have convergence in distribution. So we have a sequence of copies that are defined on the same probability space. Let me write here like n, well, copies of these processes. I will write like n calligraphic of lambda t minus lambda t divided by square root of lambda and n lambda t minus lambda t that converge almost surely to, okay, to copy of this process in which space? So D0, I forget to explain what is D0 infinity. 0t, 0t, 0t times Skorokhod space D0t. And we know that these two processes are continuous. And we know that if processes converges in, if the sequence of functions converge in this space to a continuous function, then we have uniform convergence. So this converges uniformly to this process, and this converges uniformly to this process. So they difference converge uniformly to the difference of two Brownian motions. So n lambda t minus n lambda t over square root of lambda converges uniformly on 0t to b of t and to difference of Brownian motions as lambda goes to infinity. Almost surely. So difference of our initial processes, they have same distribution, so we have convergence in distribution of n lambda t minus n tilde lambda t over square root of lambda to difference of two independent Brownian motions. And the last maybe step to make this formula a little bit more beautiful is this. This is a process. This is a process with independent increments and stationary increments, and increments are Gaussian, and expectation is 0. And variance is what is the variance of this process? Brownian motion. Yes, 2t, and well, small exercise that this process has the same distribution as square root of 2 times Brownian motion. So let me take, right, okay, this t in 0t. So prove that this process has this distribution, so the limit of these two processes is square root of 2 times Brownian motion. Questions?
So in the end, we proved even convergence uniformly?
No, we proved convergence of copies in the topology of uniform
Yes,
convergence.
of copies, and when we go back to originals,
Yes,
it's
so we have uniform convergence. So we have convergence in the space D. So uniform convergence implies convergence in the space, in Skorokhod space with Skorokhod topology. So this implies, indeed, you're right. I can write here converges to this in D0T. Yes, and if you...
But can we stay in even more strong result? So left uniform but weak, or not?
that we have weak convergence in the space D with uniform topology.
Yes, yes.
Uh, well, this is true. This fact is true, but you have to prove it maybe without another arguments. Because D with uniform metric is not separable space, and then you can't apply Skorokhod theorem. So you see, yes, you well, it is possible. It is not difficult, but the aim why I used the Skorokhod theorem was to recall it. And this theorem is very effective because very often it's easy to work with almost sure convergence, not with some abstract convergence in distribution. And if you know that certain functionals are continuous, then you are done without any problems. And let's consider next example. We see here that well, we consider intensity lambda for Poisson process, but we divide by square root of lambda, like square root of variance. And now the question is, let mu be, say, a lambda plus b square root of lambda, where a is positive number and we will send lambda to infinity. Let's consider the process n mu of t, and we subtract lambda t and divide by square root of lambda. The question, what is the limit of this? So this parameter is not lambda, but well, some lambda times a constant, so it is not a problem. And another one, and another one, plus something else. Oh, I promised you several times to say what is metric on top on Skorokhod space D0 infinity. So we introduce metric here similarly to the space C0 infinity. And the metric D0 infinity between two Cadillac functions f and g can be defined like this. Integral from 0 to infinity, distance between f and g on 0t, minimum 1 times e to the power minus t dt. So if you have convergence, so immediately you may see that if you have convergence for almost all t of fn to f on 0t, then you have convergence in this metric, and vice versa. If you have convergence in this metric, then you have convergence on almost all intervals from 0 to t. Maybe not for all. Maybe not for all. It would be interesting to discuss this, and it's interesting exercise to discuss for which particular t you have convergence, if you have convergence on 0 infinity. Well, but let's discuss this question. Okay, return here. And this process has the same distribution as n a lambda t plus n b square root of lambda t divided by square root of lambda, oh, excuse me, minus a lambda t. Minus a lambda t. Where these and these are two independent Poisson processes with intensities a lambda and b square root of lambda. And now let me write this as n a lambda of t minus a lambda t divided by square root of, a lambda times square root of a plus n of b square root of lambda t divided by oh, excuse me, and let b also be positive. Divide by square root of divide by b square root of lambda times p. And these two processes are independent. And the first question is, what is the limit of this? Brownian motion. And what is the limit of this? Игорь, Геннадий?
Brownian motion.
No. We have the same parameter here. And at the beginning of our lecture, we discussed that this process converges locally uniformly to t. And this has the same distribution as n lambda of t divided by lambda. Okay, let me write another parameter, lambda mu, for example. So if you consider Poisson process with certain parameter, and you send these parameters to infinity, then you have a convergence to t uniformly in probability. So this uniformly in probability, so this is our new, this converges to t. And okay, maybe one additional step, and I leave this step to you, that this, the limit of this process is square root of lambda times b of t plus b times t. So this process where b is a Brownian motion. Well, a small exercise. Think what happens if b is negative. Or if you consider this parameter mu, then we cannot make this step directly. So we cannot write here minus b. There is no Poisson process with negative intensity. But the answer will be this. You have to, so this is exercise. You have to find arguments. Okay, and well, we considered many functional theorems for Poisson process, certain scalings we obtain as a limit of a Brownian motion and or a Brownian motion with drift. And let me recall you that we have studied Skorokhod reflection problem for stochastic processes. And well, we know that Skorokhod map is continuous. So if certain is continuous in supremum norm, so if you have convergence of processes, well, xn may be catalog, but x be continuous process, x is continuous, then Skorokhod map of xn converged to Skorokhod map of x. Gamma is Skorokhod. And the question is this. well, exercise for you is this, and I strongly recommend you to make. Make a picture of the following two processes. Make a picture of n lambda t minus lambda t, well, divided by square root of lambda, and the process lambda t minus n lambda t over square root of lambda. And the same for Skorokhod reflections of this process and of this process. And discuss interpretation, maybe from economics or physics or something like this, or some problems of real life. We stop the topic Skorokhod reflection, and the next question is called generalized Skorokhod reflection problem. Okay. Let me recall what is usual Skorokhod problem, Skorokhod reflection problem. You have a function, say w, and you have to find a pair x and L of two functions such that, so x will be a reflection of w, that x of t is non-negative, x of t is equal to w of t plus L of t, and that the process L is non-decreasing, starts from 0, and well, and it may increase only when this process x hits 0. So mathematically, this was like this. If x is positive, if x is not 0, then L does not increase. So the LS is 0. So this was Skorokhod reflected problem. We made certain pictures that W. So when before W hit 0, X is W and L is 0. When W hit 0 and want to pass through, L is push at 0 another direction. So imagine that the robot walks according to certain program, and then it hits the wall located at 0. And if the robot wants to go down, the wall pushes up, and robot stays near the wall. And we even found formula for X and L. So, but let me write you the picture of L. So here, robot wants to go down, the wall pushes up, and this push is described by this function L. You stay near 0, and then your program is go up, so you go up until the next visit to 0, and you wish to go down and you stay near the wall, and so on and so forth. And there was a formula for the solution. L of t is so-called running minimum of W. Minimum 0 as in 0 t, and x is W plus this. Now let's consider another model. Assume that when you hit 0, then you can be pushed up by a jump. So this reflection is in some sense continuous. And now we consider the model when the effect of wall may be like this. You push from the wall according to certain function, which may be discontinuous. Okay, let me formulate the definition. So let W be a Cadillac function. Be okay. Be yes. Yeah, no. Be continuous function. Be continuous. And f be strictly increasing. And Cadillac function. And we assume that f of 0 is 0 and f is unbounded. We say that a function x is a solution to generalized Skorokhod reflection problem. If the following conditions are satisfied. The first, x is Cadillac and non-negative. Negative. Second, x of t, excuse me, x and L is a solution to generalized. X of t is equal to W of t plus f of L of t for all t. And the third, L can increase if and only if x hits 0. So L does not increase if x is positive. So integral from 0 to infinity, indicator that x of s greater than 0 dls is 0. Well, so what does it mean? Again, W is like program of robot, this blue line. Sometimes when the robot hits the wall, so the wall resists. And L of t is certain like inner time of the wall. So wall thinks and it has its own function f, and it uses this own function f and pushes the robot up, and L stops increasing if the process is positive. So L may increase only when the process hits 0. So let me make a few remarks and make a picture of a solution, and then we will formulate a theorem about existence and uniqueness. At first, if f is continuous on 0 infinity, then we may write this. Okay, if f is continuous, then and xl is a solution, and xl is a solution to Skorokhod problem, to the usual Skorokhod problem, then observe that x and composition and f and l of to generalize Skorokhod process, then composition x and fl is a solution to the usual Skorokhod problem, Indeed, x is non-negative, f is a sum of these. Oh, I forgot to write that L of 0 is 0 and L is non-decreasing. Composition F and L is non-decreasing, yes. Composition F and L at 0 is 0, because L of 0 is 0 by definition, and F at 0 is 0 by our assumption. So the only thing, is it true that if x is positive, then this integral is 0? Yes, it is, because is a solution to if L does not if L does not increase where x is positive, then this composition is also. So is it possible now to find L? Yes. L of t, you may take let me write then f of L of t is then running minimum of w and 0. So L of t is inverse of this function, minimum of w of s, minimum 0, and that's all. And since f is continuous and strictly increasing, the inverse functions indeed exist. And well, so in this case, in case when f is continuous, generalized Skorokhod problem and usual Skorokhod problem are the same. So x is the same. But if f is discontinuous, then the formula will be different. And by the way, now we even don't know, is there a solution or not? But let us make just certain guesses. What is the form of solution? Well, this function is w of t. And assume that the function f is this. So this is 45 degrees for simplicity. So it grows, then it jumps, then it grows again, then it jumps, and okay, it has certain jumps. And now x of t should be the sum w of t plus f of L of t, and we have to guess what is x and what is L. So there are no problem before the process hits 0. Then x is equal to w. Then at the point 0, you add f of L. Well, and f of L is just linear function. Is equal to just L of t. So it like Skorokhod reflecting problem, usual reflecting problem. So x should be here. The process L of t is like there. So you wish to go down, you wish to go, so the process L, he pushes you up. Your position is sum of blue line and red line, so 0. But what happens when L reaches this level? Okay, reaches this level. Then the function f has a jump. So the process stays near 0, stays near 0, stays near 0, and then f jumps. So at this moment, our process has a jump. So x must have this jump. And immediately x becomes positive. X becomes positive. Well, and we goes according to this process. So now L should not increase. Okay, so this term is a constant. And what are increments of x? They coincide with increments of w. So increments of w are like this. Oops. Like this. And then you go down. So two parallel lines. And you hit 0 again at certain point. So L is this until this moment. And then you wish to go down. You wish to go down, and what are increments of L? Again, like increment of L should be equal to increment of F and L here. So you wish to go down, you use this path, you stay near 0, L increase a little bit, and then you say, oh, go up. So you go up and you go down until this moment, and then you wish to go down, and you still use this function L, and increments of composition F and L are the same like compositions of L. So you stay at 0, and the picture of L is like, so compensation is like this, until the next jump. Okay, until the next jump. So let me make this picture like, okay, assume that the picture is this. So you wait until this part reaches this level, and then you make a jump up. Oh, okay, so let me continue. So L was like this, and then L increased, and then L made a jump, and X makes a jump, and it jumps equals to this. And then you use these increments of W and so on and so forth. Well, so theoretically, if f has a simple structure like linear function jump, linear function jump, linear function jump, then you may consider, then you may construct a solution to generalized Skorokhod problem in the following manner. Sometimes you have usual Skorokhod reflection, but sometimes you jump. Then again, you continue and make usual Skorokhod reflections, and then make a jump, and so on and so forth. Fortunately for us, there is a formula for solution to Skorokhod, generalized Skorokhod reflection problem, and let me formulate the theorem. So if W is continuous, f strictly increasing, f of 0 is 0, f is unbounded, and f is Cadillac, then and W of 0 is non-negative, then there exists a unique solution to the generalized Skorokhod problem. Moreover, there is a formula. L of t is equal to generalized inverse of f and composition with running maximum of Brownian of W. So m of t is minus minimum of W of S minimum 0. And X is a sum of W plus F and composition with inverse and this running minimum. And let me recall you that the generalized inverse of F is defined as follows. So the inverse of F is infimum of y such that f of y is strictly greater than x.
Okay,
Yes.
Why we need a generalized inverse if we mention that f is strictly increasing?
Yes, sure. If f is continuous, then generalized inverse is the usual inverse.
Mm.
But if f is Kadlag, then f the inverse, the generalized inverse of f, and f is not the usual one. So this composition is not identity. So f of f inverse is not x. And by the way, we see from this formula that if f is continuous, then this is usual inverse. Then this composition is just identity, and we have Skorokhod formula. Well, I will not prove this theorem. I will send you a book, and you can find the proof of uniqueness there. Well, and existence can be seen. Okay, and you can find existence and uniqueness, but the fact that this function is indeed a solution to generalized Skorokhod problem can be seen. So let me make a picture of inverse of composition f and inverse of f, and so you will see that the fact that x is positive is non-negative is almost obvious, and the fact actually that this function is continuous is also true, and this function is okay. It's non-decreasing. It's clear. It's clear because this function is non-decreasing. This function is non-decreasing. So this function is non-decreasing. And you have to verify that this function do not increase if x is positive. Well, but let's make pictures and discuss. Well, f is good luck function, and strictly increasing. So what is generalized inverse? Okay, this is x, this is x, this is f of x. On this interval, when the function f is continuous, and recall that f is strictly increasing.
Excuse me, can you hear
Yes,
me?
yes.
I suppose, or I have problem with connection, or you. I have freezes for several during
I
this
don't
lecture.
know. I'm sorry. Gennadian, do you have problems with connection?
Yes, occasionally.
It's like
Maybe.
for some seconds, yes?
Yeah, so maybe I have problems with internet, but I don't know. I cannot solve this problem. So here, generalized inverse is equal to usual inverse. Indeed, so what is the inverse of, let me write in this manner, inverse of y is infimum of x such that f of x is greater than y. So this is y. This is x. So this is, if this is y, this is f inverse of y. Indeed, so we find the first x such that such that infimum of all x such that f of x is greater than y. If you take points greater than this one, then f of x will be y0, x0. Then f of x is greater than y0. If you take points less than this point, then f of x is strictly less than y. So there is no problem. Assume that y0, now consider the following picture. Assume that y0 is here. What is generalized inverse? I state that generalized inverse is this point. So if y is here, then generalized inverse is here. Indeed, if x is less than x0, then f of x is less than y0. If x is greater than x0, then f of x is greater than y0. So for all y on this interval, its generalized inverse is this point. And again, if y is here, then this, and so on and so forth. And if you make a picture, it's like you have to look at this graph from this side, and then you will see the picture. So it's like flipping with respect to bisectries of this quadrant. So the generalized inverse has this form. So this, then it stays like here, then this, then this part, and so on and so forth. By the way, it can be seen that if f is strictly increasing, then generalized inverse is continuous and non-decreasing. Well, it may be, by the way, seen that composition of generalized inverse and f is y, but be careful that composition of this and this function is not x in general. I will make a picture of this graph, and we will see that if f is discontinuous, then it is not. But it can be explained in the following manner. This function is discontinuous because f is discontinuous. So it cannot be x. Well, and now here I make a picture of the function of the composition f and inverse of x. So here is x, and I will make this picture. At first, So this is a line y is x. Mark yeah. Mark these points of jumps, these, this, and of this jump, and of this point, and this point. And the picture of F and general composition of F and generalized inverse is this. X here, then a jump, then you stay, then the function is constant. At this interval, it equals to x. Then the jump and the size of jump is this. Then this. And like jump and here. So something like this. Well, if f has only finite number of jumps on each interval, then it can be easily seen by considering all segments and finding the composition. Well, sometimes, well, f may have infinite number of jumps on each non-empty interval. Then certainly you cannot say that it grows and it jumps. Well, composition will have infinite number of jumps. But what do we see? We see that this function is non-decreasing, Cadillac, and it's greater than x. So actually, well, we know that this function is non-decreasing. The first corollary is this. This is greater than or equal to w of t plus m of t. Is greater than or equal to solution of Skorokhod, usual Skorokhod reflecting problem. And we know that this is non-negative, so this function is really non-negative. And the last thing to verify that this function is solution to generalized Skorokhod reflecting problem is to prove that L does not increase when x is 0. When x is positive.
For L, we take this inner function or what?
Please repeat, Igor, I didn't hear.
What do you mean for L?
This is L. So this is L.
Okay.
So this is formula for L. So to prove that this function is solution to generalized Skorokhod is to prove that this integral is 0. And we see that well, this is a function of m of t. this function does not increase if m is not increasing, and m is not increasing if x is greater than 0. So this function is not increasing if m is not 0, and that's all. Well, and so corollary is the following. We we see that there is a formula for generalized Skorokhod reflecting problem. Well, we don't know. Is it a continuous function of W and of F or not? We will discuss this question next week. But this formula and this approach may be very useful when we approximate Brownian motion by random walks. And if we have jump reflections from 0. Well, let's consider at first simple random walk. But when you hit 0, let us exit by very large jumps, by say random variables that do not have expectation. And then again, plus minus ones with a probability 1/2, and then second exit up and xi2 copy of xi1 where xi2 does not have expectation, and so on and so forth. And we consider this Markov chain and then make a Donsker, and then we consider Donsker scaling limit. And the question is, what is the limit? Well, we know that if expectation of xi is less than infinity, then the answer is reflected Brownian motion. But if expectation of xi is infinite, maybe the limit will be like this. It's Brownian motion with certain jump time reflection from 0. Well, generalized Skorokhod problem constructs somehow. So you see, if you work naively, then, and if the limit of this exists, then in a limit, increments of the limit process above 0 should be like increments of a Brownian motion. But jumps from 0 maybe like for generalized Skorokhod reflected problem. I will tell you a few theorems on this topic, and another question is, well, what will the process f be? So we may guess that in a limit you will have Brownian motion with generalized Skorokhod reflection with certain function, random function f, which is strictly increasing. Okay, but this will be next week. Thank you for your attention.